All right, so today we're going to finish up with searching and sorting. Remember, if you're online, we are on Piazza. If you have any questions, you can post there. Otherwise, we're going to finish up by looking at a couple of searching and sorting algorithms, some that you're already familiar with, some that you got familiar with yesterday in lab. I'm going to give you a general technique here for analyzing recursive algorithms. Let's see, to go back over here, let me go ahead and get rid of this, move that up there. There we go. So remember that we have this binary search recursive version here, where you are given the array, a key that you're searching for, which is pretty straightforward, and then a left and a right index. Remember, you start at the endpoints of your array, you move this over, you move this over, you move this over until you zero in on what you're looking for, or you go past each other, and in which case you say that it was an unsuccessful search. We briefly went through an overview of how you would go about identifying the 5 steps here, where of course clearly the input is A, the size of the input is N, or more accurately the size of the range that you are searching for, searching in that particular iteration, or in that particular recursion. And the elementary operation, we settled on the fact that we are doing 1, 2, 3 comparisons, but we winnowed that down first of all to 2 because that third comparison, well, that's just an else statement. We don't need an if there at all. And then we winnowed it down all the way to 1 because, well, really in the end, it's just a call to a comparator function. And once you've got that, less than 0, greater than 0, or 0, that's an artifact of what's necessary for the control structure of the algorithm. But the problem here is that it's not straightforward in that we don't have a for loop or a while loop that we can analyze. So and then set up a summation, and then find a closed form solution, and then go all the way to step 5 here, which we already know to be log n, right? So how are we going to do this? In general, when you've got a recursive algorithm, you can follow the following steps. So analyzing recursive algorithms, ... right? Fix that later. Generally, you set up a recursive, first, let's go ahead and go with 1. You define a function that captures the idea of work, or the elementary operation, right? We're just going to set that function up and say that this function is equal, that given this input, it equals the number of comparisons made by binary search on an array of size n, right? Then you set up a recursion, right? You capture the notion of how much non-recursive work you do, and then how much recursive work you do, right? And I'll show you that here as an example in a second. 3, you solve the recurrence, or you use what's called the Master Theorem. And I've got that in the background here, and we'll take a look at that in a second, okay? Again, we are on Piazza. If you have any questions, go ahead and post there. Otherwise, let's do that for this binary search algorithm right here. The first step, of course, is that I'm going to define a function that captures the notion of work. And here we already identified the elementary operation to be comparisons. So I'm going to call my function C for comparisons. And I'm simply going to define it in English here so that I can then later translate that to math. This will be the number of comparisons made by binary search, bin search, on an array of size n. All right? Remember, n is our input size, so that's going to be the input to our resource function or our complexity function, however you want to look at that. All right? So let's go back over here and ask ourselves, how much recursive work do we do? How much non-recursive work do we do? So just look at this algorithm right here, And we kind of already answered the second question, right? How many comparisons do we make on an input size of n non-recursively? Well, again, we went through that process of 1, 2, 3, but we winnowed that down to just 2 because that last one's completely unnecessary. And then we said, without loss of generality, you can go ahead and combine those into 1 because it's going to be a call to a comparator. One call to a comparator function. After that, it's just branching in your program, right? So, one non-recursive comparison plus how much recursive work do we do, right? Let's go back over here. So we're making 2 recursive calls, right? There's a recursive call, and I've just shortened it up to BS here. There's a recursive call on the left partition if you need it. There's a recursive call on the right partition if you need it, right? Of course, there's no recursion here if you find what you're looking for and you output m, right? Can we assume the best case scenario? The best case scenario here would be binary search. The thing you're looking for is right in the middle and you're done. You made 1 comparison overall. No. So we're going to assume that it is a worst case scenario, that you have to recurse. You have to recurse until you don't find the thing that you're looking for. Okay? So we have to do these recursions. But do we have to do both of them? If, else if, else if. That tells you that these are mutually exclusive, right? So there's at most 1 recursion, okay? Now, that recursion is going to be captured by this function right here, right? So, plus C on something for 1 recursive call to binary search. Right? We're only making 1 of those. If we were making both of those calls, and as we'll see here with other algorithms, then we'd be making 2 calls and we'd be branching out, right? But now, how big is the input size when we make that recursive call, right? Remember that if we search on the left half, and do I have a picture here? Yeah, here we go. I've got a picture of it. If the thing that we're searching for is less than the middle element, then we search in the left half, this thing right here. If it's greater than the key is greater than the thing that in the middle, then we search on the right half. Right? In either case, we're only searching this half or this half. How big is that? If the entire thing were n to begin with, then this is only n divided by 2. Right? N divided by 2. So, but the array is cut in half. Right. So let's combine both of these things into 1 recurrence. C sub n, again, is the number of comparisons made by binary search on an array of size n. We have 1 recursive call, but its input is half as much as originally was there. And we're making 1 non-recursive comparison. Okay? Now, all we need to do is go to step 3 and solve this recurrence. This is, if you're interested, this is a non-linear, non-homogeneous recurrence relation. And you can solve it by a couple of techniques, by unrolling it, basically. For example, you can unroll this into C. If I plug this thing back in over here, what do I get? I get C sub n divided by 2, in other words, divided by 4, plus 1, plus 1. Right? Basically, I just expanded this out. Right? Do the same trick. Take this and plug it back in over here. And what do you get? C sub n over 8 plus 1. And then that's me expanding this out, plus 1, plus 1. And then getting rid of unnecessary parentheses. Right? Dot, dot, dot. Until you get down to what's called your base case. What's my base case with respect to the pseudocode? when the left and right indices have passed each other, right? In which case, do I make any comparisons here? Nope. So my base case is going to be, C sub n, or C sub, on an input size of 0, you don't make any comparisons. So all I have to do is get this term right here down to C sub 0, right? And you'll eventually get there because 1 divided by 2, you truncate that, you floor that, and you're left with 0. So you will eventually get there. But how many 1s do you end up adding on the way there? That's if you want to solve it. I'm going to stop short there, and I'm not going to finish that solution. Instead, I'm going to show you another way of doing this, using the Master Theorem. Now, don't worry about this. This is theta, but it's equally true that it's big O. Just replace this theta here with big O. Right? The Master Theorem states that if you have t sub n as a monotonically increasing function that satisfies these conditions, in other words, you are making A, recursive calls on an input that is cut in B segments, right? Or cut into B segments. If B were 2, then you're saying that it's being cut in half. If B were 3, then you're saying that it's being cut in a third. If B were 10, then it's 1/10 of the original, right? Plus F, where F is some function that is capturing the idea that you are doing non-recursive work, right? And then, of course, you have, it doesn't have to necessarily be T sub 1, but that's what I put here, that you have some base condition. In other words, you can't infinitely recurse, right? And you could write an infinite recursion. Eventually, you'll get a stack overflow, but whatever. You've got some other additional considerations here. Don't worry about those. But basically, you have 3 conditions here, right? If A is strictly less than B to the D, that's capturing the idea that you are making more recursive calls than you are, or sorry, fewer recursive calls than non-recursive work. If A is equal to B to the D, then that means that you're roughly doing the same amount of non-recursive work and recursive work. If A is strictly greater than B to the D, then that means that you're doing more recursive work than you are doing non-recursive work, right? F of n here has to be bounded by a polynomial n to the d. So at this point, it's just plug and chug, right? All you have that is our let's see, let's go back over here. Yeah, let me go ahead and rewrite it when we get back over there. Is our recurrence that we developed from binary search, does it conform to this formula right here? Right? So again, let's rewrite it. Oops. C sub n equals 1 recursive call on an input size that is half the size of the original plus 1. Right? It certainly looks like T sub, this thing right here to me. Right? Let's identify A, B, and D. So what is A in this case? A is sitting out front right here. Implicit. It's 1. What about B? That's pretty straightforward. It's 2. What about D, right? And when I say D, I mean look at this function. F of n is 1. In other words, the amount of non-recursive work we do on one recursive iteration doesn't matter, depend on the input size. You do one comparison. If you have an array of 1 million elements, you do one comparison. If you have an array of 10 billion elements, you do one comparison. Right? Is this bounded by some polynomial n to the d? Remember, you can have constant algorithms, order 1. Order 1 is equal to what? N to the 0. Right? So for D being 0, it conforms to this Master Theorem here. All we have to do now is look at which one of these cases applies. So A versus B to the D. When I start plugging and chugging these things, I get 1 is equal to 2 to the 0, or it is, I jumped the shark there and I just said equal, right? Y, 2 to the 0 is going to be 1, right? So which case applies? The second case. And we have that our recurrence is order n to the d log n. So by case 2 of the Master Theorem, MT, we have that C sub n, the number of comparisons made by binary search on an input of an array of size n, is equal to order n to the d log n. Remind me though, what is d again? 0. So it's just log n. That entire thing disappears, right? Because it becomes 1. So, there we go. Let me just move it over. Log base n, base 2 of n, etc. Right? Great. We didn't end up having to solve anything. Now what I want to do is I want to look at the quicksort algorithm that we sort of covered in Computer Science 1 and that you transcribed, say, from Pseudocode or from some other source yesterday in your lab in order to get it to work. The idea here is that you partition, right? So I'm not going to go over the Pseudocode because you did that already in your lab yesterday. Instead, let's go ahead and just make there's an array. The idea was that you choose a pivot element, and the pseudocode that we gave you says choose the first element to be your pivot element, right? And like a pivot foot, you clamp that down and you go around that pivot foot. You put anything that is less on one side, or on this side, and you put anything that is greater on this side. Right? So what did that look like as far as the code goes, or that you developed, that you transcribed? We started over here, and we started over here on the other end with I and j. If this was less, we simply incremented I. Right? Because in some sense, 7 is on the correct side already. 8 is going to go somewhere in here. Right? 8 is less than, or 7 is less than 8, so it's on the correct side already. Okay? 10, however, is on the wrong side. 10 is larger than 8, so it needs to go into the right partition. So we stop there, and then we continue with j. J is less than 8, our pivot element. So it needs to go onto the other side. Since 10 needs to go on the other side and 1 needs to go on the other side, what can we do with them? Swap them. Oops. 1 and 10. And then we continue. I will go over here. It's on the correct side, 2. I will advance to 4. It's less than 8, so it's on the correct side. And then it'll finally go over here. Oh, 11, it's on the wrong side. So j will start decrementing, right? And it immediately stops because now you're pointing at the same thing. 11 is on the correct side, so what happens is there were 2 cases at the end of the pseudocode. It says that either you need to swap this pivot element with the current element at which you met in the middle, or you need to look at this element and then swap it. Well, which one do we need to do? 4 and 8. And you are left with, 4 and 8. There's my pivot element. Get rid of this. And you can see that we've just partitioned around that pivot element. Everything on the right-hand side is greater. Everything on the left-hand side is lesser than 8. 8 is where it belongs. Right? 8 is where it would belong in the final sorted version of this. Okay. That was one partition, right? That was the partition subroutine. How many comparisons did we make there? In general, if I think about this as n elements, and I choose my pivot element over here, and I and j will eventually meet in the middle. on each one, I need to say, is this less than P or greater than P? Less than P or greater than P? Less than P or greater than P? Once I find two things that, and the same thing on the J partition, J side, is it greater than P or is it less than P? Greater than P or less than P? Once I find two elements that I can swap, I continue until I meet somewhere in the middle here. Right? So I'm comparing the pivot element to everything else. How many comparisons do I make in that partition subroutine? N minus 1. So, number of comparisons made by the partition subroutine is N minus 1. Right? That's basically our non-recursive cost. Remember what quicksort does now. Let's come back over here to this example. That was just the first iteration of quicksort. What do we do now? We do quicksort on the left partition. We do quicksort on the right partition. Right? So there are two recursive calls. Right? There are two recursive calls. Right? One for the left, one for the right. Right? The trick here with quicksort is it a nice even split? In this particular example, we had 4 on one side and 2 on the other. Right? So sometimes, you can imagine that if we had chosen a pivot element here that ended up being the minimum or the maximum, what would that have looked like? The pivot element is the minimum, so it goes over here. Everything else gets shoved over to that side. Right? We make one recursive call on that side. What about the other side? It's 0. We don't even bother making the recursive call then. Right? We could get lucky though. Right? If I wanted a perfect partition, if I wanted 3 elements over here and 3 elements over here, then what's my ideal choice of pivot element to ensure that? In this particular case, it would be 7. And in general, if I perfectly partitioned it so that there were exactly n divided by 2 things over here and n divided by 2 things over here, what would be that guy in the middle right there? What is my ideal? If you have a set of numbers, what's the thing in the middle? The median. Good. Right. So let's look at these two cases. And I'll immediately label them as worst case and best case. Worst case. The partitioning is uneven. Right? It results in an empty partition and no recursion and a partition of size what? How big is that partition going to end up being? If I have one element and it's the minimum or it's the maximum and I shove everything else onto the other side, how many elements are there generally? There were n before, so now there's going to be n minus 1. Good. Let's set up a recursion for that. Let C sub n be the number of comparisons by quicksort on an array or a collection, whatever, array of size n. Right? In the worst case scenario, we make no recursion here and one recursion on an array of size n minus 1. So C sub n minus 1. All right? How much non-recursive work did we do to get there? N minus 1 comparisons. This is the pivot, the partition subroutine. And this is the one recursive call. Okay? Now, does that conform to our nice little master theorem over here? Remember, I have to cut the input size in half or in 1/3 or in 1/10 of the original. Does that look like it, that I've done it right here? Nope. So I can't use the master theorem in this case. In the worst case scenario, I can't use the master theorem for quicksort. Instead, I actually have to solve it. So, spoiler alert, solving C sub n equals C sub n minus 1 plus n minus 1 leads to ... C sub n being order n squared. Right? And in fact, here's the easy way of looking at it. N minus 1, well, you've put everything over here and you found the minimum. N minus 1, you found the second minimum. N minus 1 left. N minus, the third minimum, you found where that belongs. N minus 3 now, right? Sound familiar? It's no better than selection sort. In fact, it's exactly selection sort if you're always selecting the minimum element as your pivot element, right? And we all already know that selection sort was order n squared. Right? All right, let's be a little bit more optimistic. Right? We can't always assume the best case scenario, but we can roll the best case and the average case into a reasonable scenario. You're not always going to get a bad partition where everything is on one side and then there's nothing on the other side. But the ideal is the median. So let's go ahead and assume the ideal. Right? Assume the pivot is the median. Always. Right? Then how will we end up partitioning? So partitioning, that's going to be n minus 1 comparisons. And then we now have two partitions. N minus 1 over 2. There's a smoothness rule that we can use to get rid of that minus 1. Forget about it, right? So n divided by 2 of size, n divided by 2 each. And we end up making one recursive call on the left partition, one recursive call on the right partition. So we end up making two recursive calls. So altogether, that gives me C sub n is going to be C sub n divided by 2. This is the left partition, left recursion, plus C sub n divided by 2. This is the right recursion. And then to even partition it meant that we had to have n minus 1 comparisons. Well, these two terms are exactly the same. So I'm going to go ahead and combine them into 2 C sub n divided by 2 plus n minus 1. And now, is that in the form that we can get and use the master theorem on? Yep. What's my A? What's my B? What's my D? I'll go ahead and put it off to the side here. Right. What's my A? How many recursive calls do I make? 2. That's right here. What's my B? 2. I cut it in half each time. How much non-recursive work am I doing now? How would you characterize n minus 1? You would say that this is order what? N. In other words, what's my exponent right there? 1. I'm just not writing it. Okay? So A versus B to the D. Or plugging and chugging. 2 versus 2 to the first. They're equal. And so by case 2 of the master theorem, by case 2, I have that C sub n is going to be order n to the d, but we already said that d was 1, so that can just be simplified to n log n. Right. And now you can see why quicksort is called quicksort. It's quick, on average, in the best case scenario, right? In this particular case, the worst case scenario is going to be actually really, really rare. How are you going to get, I mean, if you are lucky or unlucky enough to always select the minimum every single time on every single recursion, go out and buy a lottery ticket or whatever. It's bad luck, I guess. So whatever. It's well, yeah. You look at it as it already being sorted, right? So you can take care of that by, checking, right? There are aberrant other inputs where you get unlucky every single time. For example, you could choose the minimum, then the maximum, then the minimum, then the maximum, and you're always going left and right on your partitions. So there are other scenarios where you can't just detect it and program it away. But in this particular case, looking at the average is pretty darn good and pretty reasonable. It's much more reasonable to look at the average or the best case in this scenario than it is to look at the worst case, that you're always getting unlucky. Okay? So 2 applications of the Master Theorem. Let's look at one third and final one. Merge sort. So I'm going to give you the idea, and we might, we have enough time here, we can develop some of the pseudocode if you want to. Merge sort, the idea here is that we do with quicksort, we did the partition and then we recursed. Merge sort takes the opposite approach. It recurses and then does its non-recursive work on the way back up from the recursion. So to show you what I mean by that, let me go ahead and give myself an input here. And one more here, 2. Okay? So this is, say, an array. Right? What we're going to do is we're going to break this down and break it down and break it down. I'm going to break this down into 2 subarrays, roughly of equal size. 5, 7, 3, 4, and 8, 10, 1, 2. It's a divide and conquer approach. If we divide it enough, then it's trivially conquerable. Let's continue to divide this. 5 and 7 and 3 and 4. Right? Let's divide it one more time. 5 and 7, treating those as independent arrays. And 3 and 4. So we can't divide it anymore because we can't have an element, a half an element, right? But what we can do is we can start, what can we say about this array right here? It's an array of size 1. So by definition, what? It's sorted, right? And you could do so what you're going to have here is 8 sorted arrays. Now what we're going to do is we're going to start merging them together. Right? So fast forward, fast forward, fast forward. Let's look at what it looks like when we've returned back to this step in the process. All right? Just so that we get the idea of what we're doing. There's 3, 4, 5, 7. So 3, 4, 5, and 7. And in the other one, there was 1, 2, 8, and 10. 1, 2, 8, and 10. Basically, by coming back up from the recursion, we're merging them together into sorted arrays. So when we return back up from the lower recursions, now each one of these sides is sorted. And we've got 3, 4, 5, 7, 1, 2, 8, and 10. Now what we need to do is merge them together into one big array. Same trick that we use with partitioning. I keep track of 2 indices. Right? Now I'm going to create a merged array of elements here. Which one of these should I put, I is now referring to 3 and j is now referring to 1. Which one should I put in the front? This one, right? So 1. And then I advance j. Right? Now I'm looking at 2 and 3. Which one of those goes next into my array? 2. Right? 2. And I advance j on the right partition. This is right, left. It doesn't really matter. Swap them around, you're merging them. It's like taking 2 things and zippering them up so that they're merged together into one sorted array. So 3 and 8, which one comes next? 3. and I advances to 4. Right? 4 and 8, which one comes next? 4, I advances. 5 and 8, 7 and 8, right? And at this point, I has fallen off the edge. Do we need, in fact, do we have anything to compare to anymore? Nope. So what do? We simply take the rest of these elements and throw them in. Right? Now, I did that to show you a corner case. What, in the worst case, what are we doing? This one and this one. I'm going to put this one down here, then this one. I'm always switching back and forth. I'm always switching back and forth. How many comparisons does this merge process make? We can just estimate above, right? Eventually, you're going to get down to a scenario where all of this stuff has already been merged. All of this stuff has already been merged, except for this last guy over here, right? So on each iteration, when I moved this over, I removed one of the elements and I put it into the merged array. So how many iterations did I end up doing? And there was one comparison to do that. Do I take this one or do I take this one? So which one, on each iteration I got rid of one, so how many iterations were there total? If this were n divided by 2 elements and this were n divided by 2 elements, then I'm making number of comparisons to merge 2 n divided by 2 arrays is what? I had to make one comparison for this. I had to make one comparison for this. This, dot, 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 all of these. So, n divided by 2, plus, I had to make one comparison for this, and this, and this, and this. Except for this last y, right? Once I ran out of one, then I just need to throw the rest of them in, right? So, n divided by 2 minus 1. And that's going to be what? N minus 1. Right? Comparisons. But don't forget the recursion, right? This recursion, the only way that we could do this is by getting down to an array of size 1. In which case we didn't have to make any comparisons at all. Right? So, let C sub n be the number of comparisons by merge sort on an array of size n. Right? Remember, we made 2 recursive calls, but it was far more predictable. We cut it in half exactly. Cut it in half exactly. Cut it in half exactly. Now, if you've got 9 elements, one of them is going to have 4, one of them is going to have 5, so it's plus, minus 1. Doesn't matter. The smoothness rule says that we can get rid of those. Okay? Plus n minus 1 comparisons for the merge on the way back up. Right? Look familiar? So immediately, what can you tell me? N log n. Right? That's exactly the one that we just did. Do we want to see pseudocode? Of the merge is what I would do. Really? Yeah? Okay. You've challenged me. All right, so the input is 2 sorted arrays. A, and here they are arrays. So I'm just going to go ahead and simplify it to A1 through AN and B, B1 through BM. I remember that N and M are arbitrary. By virtue of us cutting it in half each time, N and M are roughly going to be the same, plus minus 1, but this is the most general that we can get, okay? And I'm going to need both of those endpoints because you could conceivably, if you really wanted to, I don't care about merge sort, I just have 2 arrays and they're guaranteed to be sorted. I want to merge them up, I want to zipper them up. This one has 1,000,000 elements, this one has 10, right? You could do something like that, okay? My output is going to be a sorted merged array C. Right. So I'm doing this off the top of my head, so forgive me if there are errors, but the full pseudocode, of course, can be found in the CS1 book. Okay. All right, so pseudocode, I'd set up the array of appropriate size, n+1, size n+1. I'd call malloc or doing whatever, who cares about that? Let's just go ahead and codify this process. Right? I'm going to start I at 1, and I'm going to start j at 1. Right? So I at 1, j at 1. Now, I'm going to need to be very, very careful here because I and j are going to advance. When one of them falls off the face of the earth or the other one falls off the face of the earth, I need to stop, right? So while I is less than n, good, less than or equal to n because we're using one indexing, right? And j is still in bounds. And j for b is going to be for the other partition here, and so that's going to be bounded by m. Then I can go ahead and start looking at, now I'm looking at we're looking at a sub I versus b sub j. Whichever one is less, that's what goes into my my merged array. Okay. So if a sub I is less than b sub j, then a sub I goes into C. C sub, and here I'm going to introduce another variable, k. K is going to end up being a sub I. Right? Else, C sub k is going to take on b sub j. Right? So if I'm going to use the C sub k for indexing on the merged array, of course, where should I start it? 1. Right? And then, regardless of whether it goes, if it's A or B going into C, I need to increment my K. Right? I've run out of room, so I'll come back up here. When do I break out of this loop? When either I or J has fallen off the edge of its array. So what I need to do is, if I falls off the edge of its array, I need to take everything remaining in the B partition and make sure that it's put in. If J falls off, then I need to make sure that I take everything in A and I put it back in. I'm going to combine that with just two simple loops. While I is less than or equal to n, C sub k will take on the value A sub I, k plus plus. And then an independent loop after that, not nested, while j is less than or equal to n, C sub k will take on B sub j and k plus plus. Oh, and also probably j plus plus and I plus plus. Because, of course, you need to advance your I in order to get out of that while loop. This has the advantage of taking care of both of those cases. Did I fall off the edge? If so, then this loop will not execute at all, right? And then only this loop will execute. If j fell off the edge, then this loop will execute, but when we get down to this loop, it doesn't execute because j is already beyond m. And that's it. These are not nested. This while loop here has ended here, so we've got 1, 2, 3 while loops here. Now, setting up a, if we wanted to go back and actually analyze this, the way that I did this was kind of hand-wavy, and I just said, well, everything gets compared to everything else to merge. If you actually wanted to be more formal about it and set up a summation here, it's going to be a little bit difficult with all these whiles, but it's the same basic principle that you're only comparing, at most, every element gets compared to another element at most once. And then it's taken out of the game. Right? So there's my merge subroutine. Okay. Any questions on searching and sorting? Any questions on analyzing recursive algorithms? No? Okay. Then let me go ahead and get rid of this. We do have over a half hour left, and I don't want to waste that time, but I also don't want to burden you with stuff before next week. We're going to get into our last topic here, which is trees. Right? In just a second, bear with me here while I bring this up. Markdown. And so what I will do is I will give you a brief introduction here. Open a new window, and it's 2021. There we go. And this is the main section. There we go. All right, so again, what has this course been about? One of the mantras is a quote by Eric S. Raymond that smart data structures and dumb code are a lot better than the other way around, right? So it's computer science too, but one of the things that we really try to focus on is data structures. What data structures have we seen so far? List-based data structures, array-based data structures, using those two to create other data structures called stacks and queues, which is what you're going to do in your lab next week, right? What we want, though, is we're on a quest. We're on a quest for a structure that will provide efficient CRUD operations. Remember, CRUD, create, retrieve, update, and destroy. Right? Our quest is for a data structure that can hold these elements and provide efficient retrieval or search, efficient insertion, efficient deletion. The one thing that's left out here is update. Why? Because you can retrieve it, remove it, and then insert a new element there, right? So update is simply just a rephrasing of the other two operations, right? The lists that we've seen so far are linked lists and array-based lists. So linked lists. Tell me about those. If you wanted an operation to insert at the front of the list or at the end of the list, is that efficient or not? With a linked list. As long as you keep track of the tail, yes. So that caveat there, yes. If you have, it's going to be order 1 time operations for insertion or deletion or retrieval from the head or tail, right? But what's the counterpoint there? When is a linked list not efficient? When you're looking at the middle, when you're looking at an arbitrary index, right? It's going to be order n time operation for an arbitrary operation or index-based operation. Okay? So benefit on one side, if you're doing it very, very specifically on head and tail, that's why a linked list was our choice for implementing a stack and a queue, right? Because you're only ever working at one end or working one operation at one end, the other operation at the other end, right? What about an array-based list? Tell me about those. And it was same operations as before. So array-based. If it's, what about an index-based retrieval here? Order 1 index-based retrieval. Why? You just jump there, right? It's just a memory offset. It's where you have random access due to random access, right? So all you have to do is compute a memory offset. You want the 10th element. The 10th element is 10 times 4 bytes away. Jump to that memory location and you're there, right? Now, of course, that's ignoring all the engineering issues underneath where that's a cache miss. So we actually have to go to main memory to load it. Oh, it's a cache miss in the main memory, so we have to go to virtual memory on disk to load it, right? Don't worry about those. Those are engineering concerns, right? Do we have the same behavior for insertion, index-based insertion? So I have a million elements, and I want to put something right in the middle. What do I have to do? I have to shift 500,000 elements down. If I want to put something at the very beginning, I have to shift all million of those elements down, right? So this is going to end up being order n for because you have to shift elements. Right? What else could you do though? And so insertion, deletion, right? Retrieval, you could do that all day. What if it were sorted? You can exploit what? What algorithm can you exploit then if an array-based list is sorted? Binary search for arbitrary searches. Right? So if you maintain an ordering, like in the final phase of your project, and you use an array-based list to represent your sorted ADT, then you can use binary search. Not that you'll need to or want to, right? Okay, so kind of just the opposite. Linked lists are very efficient on one thing, but inefficient on the other. Array-based lists are efficient on that other thing, but very inefficient on the other, right? So what we want, we're still on our quest basically. We're on a quest for a data structure that provides efficiency on all three of these things, okay? We're not going to get all the way there. The true answer there, by the way, is a hash table. If you take Computer Science 3, you'll cover it. But we are going to look at another data structure called trees, right? Trees have the potential to offer order log n operations for all three operations. There we go. Performance. There we go. Right? Trees have the potential to offer order log n performance for all three. Right? So, that's basically binary search behavior. Binary search behavior for insertion, deletion, retrieval, and also the replacement if you really wanted to. Right? So, what is a tree, first of all? So, in real life, what is a tree? It's a plant, right? Oh, good. I like that description. It is a tree that grows from the ground and grows upwards. We're computer scientists and also mathematicians. Our trees do not grow upwards. They grow down, right? Yeah, neither are computer scientists. Why do our trees grow down? I've looked this up before. The individual that introduced the notion of trees into mathematics was Cayley. And the very original paper, which 100 and some years ago, hundreds of years ago, maybe 200 years ago, he drew the trees growing down. Why? Because our trees represent data. How do we read data? As humans, we read left to right, top to bottom. And so he made his trees so that they grew down, right? But the trees also branch out, right? So now we're branching down. If I've got a node here, branches will go down. It'll split into other nodes. Right? Think of it as a family tree. Think of it as ancestors and descendants. That grows down too. Right? Why? Because it's data. We're reading it top to bottom, left to right. Right? Introduction to trees. Computer science trees, I should say. Right? A tree is an acyclic graph. That is a graph with no cycles. Right? Oh, whoa, hold up here. Before we even get there, what is a graph? A graph is ... So a graph is not that x-y axis. I mean, it is. And then you're graphing x squared goes like this. It's a nice parabola, right? That is a graph, right? But what is a graph? A discrete graph. Oh, okay, is a collection of nodes or vertices and edges connecting nodes. Right? Good. And since I've got this, I can go ahead and start drawing things. Go on. There we go. All right. So here's an example of a graph. Right? A, oops, A, B, C, D, E. What I've just drawn is 5 nodes, or vertices. I've also labeled them, right? Ultimately, our nodes are going to contain data. Edges can also contain data, right? But there's some interconnected connection between these. If A and B are connected, then we just draw a line, and that's an edge, right? These are nodes or vertices. If this were pure graph theory, we would call them vertices. Nodes, the technical difference is that nodes hold things. They hold data. So I'm going to call them nodes. Right? You could connect them in any number of ways. Right? Now, this is a crossover point here. Don't think of these as, oh, okay, now C is connected to B. Right? That's just because that's how I drew it. I could equivalently draw it so that it looks like this. Right? All right, there. There's a graph. Right? If you wanted to draw all the connections between them, then you could. I won't, because I just wanted an example here. Is this a tree, though? No. A tree is an acyclic graph. A cycle is where you can start at one node and traverse out of that node, go to another node, traverse over to another node, traverse back to the original node. That right there forms a cycle. It's a cycle of length 3. There are lots of cycles with this example. There's a cycle of length 4 going right here. There is a cycle of 1, 2, 3, 4, 5. There's a cycle of length 5. Right? And there are lots of other cycles. This cycle, but then you can combine them into this. Is that a cycle? So, sorry, I'll go ahead and go B to A to C to D back to A. There is a cycle in it, but this thing right here is kind of screwing it up the idea. Right? Well, you could go from A to C and then right back, right? You can just, that these are two-way edges. That's not a cycle. That's not a simple cycle, I should say. Right? I could do something like this, where, okay, I go A to B, C to, or A, C, D, and then, let's go with D, A, C, back to D, then back to B. There. That's not a simple cycle either. Right? Yes, I started at A and I ended up going back to A, but I traversed a node more than once. Okay? So what is a cycle? Or what constitutes an actual cycle? A cycle, or a simple cycle, is a path in a graph that starts and ends at the same vertex, or same node, never having traversed an edge more than once. Traversed the same edge more than once. Okay? So again, was this a tree? No, because we had a whole bunch of cycles. So what I'm going to do now is I'm going to start erasing things. All right? Let's go ahead and get rid of this stuff right here. Get rid of this. Okay. I'm going to start erasing edges. Is that a tree now? Nope. That edge is still there, or that cycle is still there, that cycle is still there, etc. It's a whole bunch of cycles still. All right. Let's get rid of one more edge, or let's get rid of this one. Is it a tree now? Nope. What if I got rid of that one? Is it a tree now? Nope. In fact, it's a disconnected graph. That's still a graph. This is what's called an isolated vertex over here. You can do that, but I won't, right? Because what I want is, I still want a tree. So help me out here. Which one? C to B? C or C to D? Okay. That'll work, right? Now, are there any cycles left? Nope. So let's make some observations here. How many nodes are there? 5. How many edges are there? 4. Do you think that there's some connection there? let's try to add one more edge without making it a non-tree. Can I add this edge back in? Nope. Can I add this edge back in? Nope. That? Nope, because then it would be like this. Right. Can I add that edge in there? Nope, now I've got a bow tie pasta. Right, or TIE fighter or whatever. So can I add any more edges? Nope. So one observation is what? All right, observations. All right. A tree with n nodes will have how many edges? Oh, okay. I'll go ahead and go. You're right. A connected tree with n nodes will have n minus 1 edges. Right? A tree may be disconnected. Some nodes may not be reachable from others. Right? In which case, if I've got a tree that's disconnected, I've got 2 trees. If I disconnect one of those 2 trees, then I've got 3. And eventually I have a what? If you have many trees, you have a grove. Okay. Bigger, a forest. Right. Is it 2 R's or 1 R? Okay. All right. So our first, and there are no cycles, of course, right? Again, the whole reason that we're doing this is because we want data structures. We've got data. What we want is structure, right? So we've already added some structure here, right? One of those pieces of structure is that we've taken away all cycles. And if you've taken away all cycles, then what's another observation that we can make? In fact, let me go back to the example here. All right, a path, no, let's define it over here. I'll go back up before our observations here. A path in a graph or tree is a series of nodes that are connected by edges. Okay, that's the definition. So let's look over here. What are some paths? I can go from A to D to B. That's a path. What's its length, by the way? To travel there. Think of these as houses. I'm at house A, and then I go to house D, and then I go to house B. How many edges did I need to traverse? 2. So the length there is 2. I can go from E to D to A to C, right? So E, D, A, C. What's the length there? 3. And one single edge, by the way, is a path. I can go to A to C, and that's a path of length 1. You can talk about paths of length 0. If I'm already at home, how do I get there? Don't go anywhere. Just stand there, right? So you can have paths of length 1 because implicitly everything is connected to itself, okay? But here, is this a path? C to D to E? No, why? This is missing right here, right? So we don't have that edge. That is not a path in this particular example, right? So my question here is, do we have structure with respect to paths, since we've got a tree? If I start at any edge, vertex, or any node, and go to any other node, how many paths are there? Let's go ahead and go back to our example here, A to B. I want to get from A to B. How many ways are there of doing that? 1. Okay. I want to go from E to C. How many ways are there of doing that? 1. I want to go from A to C. How many ways are there of doing that? 1. So what's our observation? In a tree, there is exactly, in a connected tree, I should say, connected tree, there is exactly one path connecting any pair of vertices. Right? Exactly one path. Right? And so since I'm saying that it's connected, there has to be a path. Otherwise, if you've got tree, 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 you've got a forest and you're talking about something different. Okay? That seems useful, right? That seems really, really useful because it's highly structured. We start with all graphs. A graph can be anything. It can be connected in any way that you want. It could have cycles. It could have a whole bunch of garbage in it. We're saying get rid of all the cycles. We're giving it more structure. And one of that structure, the structures that we have on, and then we're also saying make it connected. That means that we've got a lot of facts that we can deal with. Why do we like structure? Because structure can be exploited, right? Why did we like the fact that a sorted array list, or a sorted array, why do we like the fact that an array can be sorted? Because we can exploit it and apply binary search for really efficient searching, right? If we've got a structure to our trees, then that means that we've got structure that we can exploit for super efficient algorithms, okay? Now, let's take this thing, and unfortunately, I mean, the marvels of modern technology and presentation software here still don't allow me to do this, but maybe in the 10, 20 years when we're all learning on VR instead, and then every virtual seat will be filled at that point, right? Instead of just YouTube telling me that I have 55 playbacks, right? What I'm going to do is, now imagine me magically taking one of these nodes, picking it up out of my iPad and letting gravity, dangling it and then letting gravity pull all the others down. What might it look like then? And I did that with D. Right? Gravity is going down now. Right? Well, off of D we had E, B, and A. So, E, B, and A, looking something like this. What else was connected to it? C was connected to A. So it would be dangling off like that, right? Dangling and organized, right? What if I took a different node here? What if I took B instead, and then I dangled everything off of it? What would it look like? B, only D would be connected to it, and then off of D, what would I have? A and E, and then off of A, C would still be hanging, right? I could do that with each node, right? And I would get a different, we call them topologies, right? Like a topological map shows you what it's shaped like. With a tree, you also have a topology, what the shape of the graph is, okay? This is called orientation. Orientating trees. Right? Now we're talking about family trees, right? And there's an up, there's a down. They grow down. You can have ancestors. You can have descendants. If we use all that terminology, what do we have? Think of it like this. I'm going to call this G right here. From the perspective of L and R. If I look up in my family tree, who do I see up there? Parents, right? So nodes may be referred to as parents or children. We've used that terminology before with respect to a UML diagram and inheritance, the parent class, the child class. We've used it with ER diagrams, with databases, the parent table, the child table. A child cannot exist without a parent, right? And foreign key constraints. You can also refer to, grandparents, parents, children if you want to, etc. Or in general, ancestors, descendants. But not only that, I've oriented things so that they are going left to right. Right? If I look at these two things right here, I'll call this P for parent. This is a left child and a right child. Right? So this orientation is up and down. The left and the right, that gives us orientation left to right. So as you can see here, we are adding more structure to our trees by dangling them and orienting them top to bottom, but also by organizing the children nodes so that we're reading them left to right, just as Kaylee did 250 years ago. Right? There's a left child and a right child. You, of course, could have many children. I have 3 children. Right? 1, 2, 3. Right? The leftmost child, the middle child, the rightmost child. Right? You could have 1, 2, 3, 50 children. And then at that point, you start indexing them. The first, the second, the third, the fourth, the fifth, etc. Right? But you always go left to right. Right? When we come back on Tuesday, we're going to add even more structure by limiting the number of children that you can have. If you limit the number of children to 2, well, that means that you can also have 1 child, an only child, or you can be the luckiest of all and have no children. Right? We have a lot of dinks in our family. Everybody knows what a dink is, right? Double income, no kids. They could do whatever they want. But we could have 2 children, we could have 1 child, we could have no children. By the way, we could have a left child or no right child, or a right child and no left child. Right? So there are lots of configurations that we can have here. This gives us what's called a binary tree. Why is it binary? You can have at most 1 or 2 children. You can have 0 children, you can have 1 child or the other child, but binary trees are where you limit it to at most 2 children. Okay? All right. I don't see any questions online, so have a good weekend.